Hello, everybody. We begin the new topic. In the third part of this course, Semiconductor Devices, we will be considering the metal oxide semiconductor field effect transistors, MOSFETs. In this lecture, I will remind you what the field effect is. I will show you how MOSFET operates in principle. I will introduce briefly the four main types of metal oxide semiconductor field effect transistors. And finally, I will begin analyzing the operation of MOSFETs using the tool that I have introduced earlier, the energy band diagram. Now, MOSFETs are the most widely used type of transistors in practical in electronics, and their operation is based on the field effect. So the reminder of what field effect is, we have already discussed field effect in the, I do not know how many lectures ago that was, but when we were talking about the Poisson-Boltzmann's equation and its solution. The field effect refers to the possibility of controlling the concentration of charge carriers of both types by varying the value of the potential on the surface on the semiconductor, and by controlling the concentration of both types of charge carriers, you are also affecting the value of the surface conductivity, sigma, which is given by this general formula. It is the product of the elementary charge times the electron concentration multiplied with electron mobility plus hole concentration multiplied with hole mobility. So by adjusting the surface potential, you can control the value of the surface conductivity. Now, in this formula, I would like to point out that the mobility values, mu E and mu H, near the surface are not the same as the bulk mobility values, because the scattering mechanisms are not the same at the surface and in the bulk. So in the bulk, the main scattering mechanisms are the interactions, the scattering of the charge carriers by phonons, quanta of lattice vibrations, and also by defects and impurities of the crystal lattice. But at the surface, you have a different kind of phonons, the so-called surface phonons. And besides, the concentration of defects and foreign atoms at the surface is usually higher than in the bulk. So the mobilities mu E and mu H have different values for at the surface and in the bulk. Anyway, suppose you have a p-type semiconductor, okay, shown here. The bulk that is far away from this surface at x equals 0, the semiconductor is grounded so that the electric potential as well as the electric field far away from the surface go to 0, and you are changing the surface potential somehow. We will discuss the ways to do that later in this lecture, but you can somehow change the surface potential. Now, for different values of the surface potential, you can have different regimes, which are found by solving the Poisson-Boltzmann's equation analytically. If the surface potential is relatively low, smaller than the thermal voltage, then you can use Debye screening theory to find that the electric potential decreases exponentially from the surface value to 0 in the bulk, and the rate at which it decreases, the characteristic screening length, is the Debye length. Now let us assume that the value of the surface potential is positive. This means that you are pushing away the majority holes, and eventually you will very quickly, at not too big values of the surface potential, you will create a depletion layer in which you have pushed away the majority holes. So the concentration of holes is much smaller than the concentration of the ionized acceptors. And at the same time, you have attracted electrons, minority electrons, but the concentration of electrons is not yet big enough, is not yet big relative to the concentration of the ionized acceptors. So you can neglect both electrons and holes in this depletion layer, your potential decreases in the depletion layer, your potential decreases approximately as a quadratic function of distance x from the surface, and the charge density near the surface is approximately constant inside the depletion layer, and it is given by the product of the negative elementary charge, acceptor ions are negative, times the concentration of acceptors. Okay, and at some point the depletion layer ends, and this is all very nicely described by the depletion approximation. Then, if your surface potential is increased further and it reaches the threshold value, which is twice the difference between the intrinsic Fermi energy minus the actual Fermi energy in the semiconductor divided by the elementary charge, you are starting to form the inversion layer. At this value of the surface potential, the threshold value, the concentration of minority electrons at the surface equals the concentration of majority holes in the bulk. So your inversion happens in the sense that your minority electrons become majority carriers at the surface, whereas in the bulk, electrons are still in the minority and always will be. So at the threshold potential, the inversion layer just starts to get formed, but it has not quite developed yet. But as you increase the surface potential further above this threshold value, you already have this inversion layer fully developed. And if you keep increasing the surface potential, the width of the depletion region does not grow anymore, but instead the size of the inversion layer and the concentration of electrons in the inversion layer increases. But the inversion layer will remain quite thin, because as the concentration of the electrons in the inversion layer is high, they are very efficient in screening the external surface potential. So the value of the electric potential inside of the inversion layer drops dramatically, very quickly, and eventually it reaches the threshold value at which the inversion layer can no longer be supported. And then the depletion region begins. And it begins when the initial value of the potential where the depletion region begins is exactly the threshold potential. And because it is the value of the initial value of the potential which determines the width of the depletion region. Remember the square root formula, which has the square root of the surface potential in it, right? It is for this reason that the depletion region width does not change as you increase the surface potential above the threshold value. Okay, so that was a memory refresher for you and for me. All right, so now let's make an important observation. By changing the surface potential, we can have the surface layer, the inversion layer on and off. If the inversion layer is on, the conductivity in this surface inversion layer is high. If the inversion layer is off, then there is practically no or very little surface conductivity. You can dramatically affect the surface conductivity by switching the inversion layer on and off, which you do by applying a surface potential. Now the only problem to solve is how to control the value of the surface potential, and this is what is done in metal oxide semiconductor field effect transistors. So behold the MOSFETs in full glory. Here is a schematic illustration of a MOSFET. It consists of 1, 2, 3, 4 parts. You have a substrate. Let's say this is a p-type silicon, and we call this substrate the body of the MOSFET. Then you have two electrodes, one here and one here, which are called the source and the drain. These two electrons are really just heavily doped N regions inside this p-type body. So you have a heavily doped N region here, the source, heavily doped N region here, the drain, and of course you have some metal plates or something attached to those N regions, so you can control the potential applied to the source and the drain. You can collect the current flowing, but all right, good. Now, if you just had the body, the source, and the drain, and they're far away from each other, then if you apply a voltage between the source and the drain, you would detect no current. But now you wish to connect the source and the drain by an inversion layer. And you do this by means of a third electrode called the gate. The gate is an electrode, a metal plate, above the region which between the source and the drain, just a metal plate. But it is not deposited on the semiconductor directly, because that would be stupid, because then the gate would, this connector, this electrical connection between the source and the drain would always be on, right? So you do not want that. Instead, that metal electrode, that gate electrode, is deposited on a thin, how thin, maybe a few hundred nanometers layer of a dielectric, which is usually an oxide. So usually these MOSFETs are made, they are silicon devices, and the most logical material for the dielectric would be silicon oxide, right? Because what else? That's smart, right? You can oxidize silicon very easily. All right. All right, so that's your MOSFET. And now by applying the voltage to the gate, positive voltage, you are affecting the value of the surface potential right underneath this oxide layer. And you can make it positive, and you can make this surface potential reach and then exceed the threshold value, and thereby you will be creating this inversion layer, which will connect electrically the source and the drain, and then the current would be flowing between the source and the drain if you apply voltage. So this is the configuration that we will be discussing. The body is grounded, the source is attached, is connected to the body electrically, and so the source is also grounded. You apply the voltage VD, with the drain voltage, to the drain. Sometimes I will be writing V sub D, the drain voltage. Sometimes I will be writing VDS, the drain to source voltage, but the source is grounded and the body is grounded, so it's the same thing. VD and VDS will be the same thing. And now, depending on the drain voltage, you will measure the current in the drain as a function of the drain voltage. In addition, you are applying the gate voltage, VGS, and sometimes I will denote the gate voltage as simply V sub G. Again, since the source is grounded, the gain to source voltage is the same as simply the gate voltage, if we have the 0 voltage at the source. All right, and here is the qualitative picture of how what the current voltage curve of the MOSFET transistor looks like, depending on the gate voltage. So initially, the current in the drain increases with the drain voltage pretty linearly, approximately linearly. So this is the ohmic regime. And then the rate of this increase gets smaller and smaller, and eventually the current saturates. And then the current doesn't change anymore. Now, in reality, it does increase very little, but we will not be discussing the reasons for that. We will not be addressing the ideality effects in this course. So this is just the initial information about this semiconductor device physics. Okay, so the current is saturates, right? And the higher the gate voltage, the later this saturation happens, and also the higher the value of the current in the saturation regime. Now we can understand this picture qualitatively, and it is this. So let's say the drain voltage is low. I apply the voltage to the gate. The gate voltage is higher than the threshold voltage. The threshold voltage is such that the value of the surface potential underneath the oxide layer is the threshold potential, twice the difference between the intrinsic and the actual Fermi energy divided by the elementary charge. Okay. Now I would like to state the obvious. I'm just doing my due diligence that the gate voltage and the surface potential underneath the oxide layer are not the same. They differ. Why? Because the gate voltage is applied to the surface not directly, but through this oxide layer. And therefore, the two parameters are different. There is a voltage drop across the oxide layer. So the two voltages, the surface potential and the gate voltage are different. All right. So, and at the threshold gate voltage, the value of the surface potential is the threshold value. All right. So, what happens at the saturation? So, at small value of the drain voltage, so in the beginning of this curve, right here, the inversion layer is more or less uniform. It is uniform and it connects the source and the drain. More or less uniform. But as you increase, when you increase the drain voltage, then the non-uniformity, the modulation of the inversion layer width comes into play. Why? Because the value of the electric potential in the inversion layer actually increases. It has the lowest value 0 at x equals 0, that is where the inversion layer begins, near the source. But then as you go from left to right, from the source to the drain, along the inversion layer, then the potential that you measure increases from 0 to the value V drain, to the drain voltage. Now, so let's say, okay, let me give you just a simple argument. So let's say the threshold voltage has the value of 1 volt. Okay, threshold voltage has the value of 1 volt, provided that the semiconductor is grounded and the value of the surface potential is 0, right? So you need to apply 1 volt to the gate. But what if the semiconductor is kept under the potential of half a volt? Then if you apply 1 volt to the gate, this will not be enough to create the inversion layer. You will need to apply the voltage of 1.5 volts, right? You need to apply the voltage which is by V sub t, by the threshold value higher than the value of the potential at the surface of the semiconductor. Locally, the value of the potential at the surface of the semiconductor, so it increases. It increases from source to the drain, from the value 0 to the value V drain. Hence, the voltage between the local point in the inversion layer and the gate, it changes from the value V gate at x equals 0, so in the left part of the inversion layer, to V gate minus V drain in the right part of the inversion layer. And it may happen that the difference V gate minus V drain, that is the voltage between the gate and the point in the inversion layer in the very right part of the inversion layer reaches the value of the threshold voltage. This means that the inversion layer at this point cannot be supported by the gate voltage anymore. And the inversion layer, a pinch off of the inversion layer happens. The inversion layer gets detached from the drain because it can no longer be supported. And of course, this happens when the drain voltage is sufficiently high. It must be, so this pinch off happens when the drain voltage reaches the value of V gate minus V threshold, because at this point, the voltage between the gate and the rightmost point of the inversion layer will be the threshold voltage, right? Now, as you increase the drain voltage above this saturation value, the right end of the inversion layer moves a little bit to the left toward the source. The inversion layer gets a little bit shorter. The pinch off happens at a point a little bit closer to the source, a little bit further away from the drain. So the inversion layer gets a little bit shorter, but that effect is small. That effect is really small. And the potential difference between the beginning and the end, or between the end and the beginning of the inversion layer, will still be this saturation voltage, which is the difference between the gate voltage and the threshold voltage. And it is constant. As you increase, okay, so as you increase the drain voltage above the saturation value, pinch off happens, the inversion layer gets a little bit shorter, the length of the inversion layer gets smaller as you increase the drain voltage, but but not by a factor of 2, not by 10 times. It's just a small percentage, a small effect. The potential difference from one end of the inversion layer to the other remains fixed, which means that electrons are pulled from the left end of the inversion layer, from the source, to the right end of the inversion layer. When they reach the right end of the inversion layer, the electrons, what do? They cannot get accumulated. They have to go further. Where do they go? Of course, they go to the drain. And so the electrons are pulled by the same voltage. They move through the inversion layer, and then they keep going through this depletion region to the drain. And the current will be constant because the resistance of the inversion layer is practically the same, and the voltage across the inversion layer is practically the same. Not practically, it is the same. All right, so that's the reason the current voltage curve saturates at this saturation value of the drain voltage. The goals of this and the next 2 lectures will be to figure out the threshold voltage of a MOSFET and to be able to analytically describe, well, approximately, but it will be an analytical formula, describe the current voltage curve of a MOSFET. So these current voltage curves. So these are our tasks. But before we proceed, I would like to explain the main MOSFET types that are used in practical applications in electronics. So MOSFETs come in four kinds: the N MOSFETs and the P MOSFETs. This letter N and P refers not, it does not refer to the type of the semiconductor used as the body. It refers to the sign of the charge carriers in the inversion layer. So if your body is of P type, then this is an N MOSFET, because the charge carriers in the inversion layer are electrons. And if your body is of N type, then this is a P MOSFET, because your charge carriers in the inversion layer are holes. And also MOSFETs, apart from the sign of the charge carriers in the inversion layer, MOSFETs can be of either enhancement mode or depletion mode. And these words mean that they tell you whether or not you need to apply gate voltage to the gate in order to create the inversion layer. So in the enhancement mode MOSFETs, you need to apply some voltage to the gate in order to produce the inversion layer. Okay. But in the depletion mode MOSFETs, inversion layer already exists even at zero gate voltage. And usually, well, not usually, I practically always, almost always, it is not really an inversion layer. It is, so you have, let's say this is a depletion mode N MOSFET, right? Like as in the lower left diagram. So this means that your body is of P type, and you have the heavily doped N plus region for the source, heavily doped N plus region for the drain, and also the semiconductor is N doped at the surface. Between the source and the drain, you have this thin layer of N doped semiconductor. So the source and the drain are already connected by this N doped channel, N channel. So they already communicate. And now your gate voltage needs to be negative, or the surface potential needs to be negative, and it must exceed a certain value in order to switch off that communication channel, in order to kind of get rid of those electrons which connect the source and the drain in this built-in channel, right? So this is the depletion mode MOSFET. And similar idea applies to the depletion mode P MOSFET, where the channel which connects the source and the drain, the built-in channel, is produced by ion implantation, by doping the surface region with acceptors. All right. Okay, so now let's start discussing the physics of MOSFETs. More precisely, we will focus on the MOS part, metal oxide semiconductor part of the MOSFET. So this part, semiconductor oxide metal, using the energy band diagrams. So energy band diagrams is a powerful tool to analyze semiconductor devices. In the energy band diagrams, you indicate the important energy levels, such as the Fermi energy, the conduction and the valence band edges, the vacuum energy, as a function of the spatial coordinate x. So let's say you have here is the boundary, what happens to the Fermi energy when I go, or with the vacuum energy if I go to the left from the boundary to the right. So we have already used the energy band diagrams to understand something about the metal oxide semiconductor diodes. Now let's complicate our lives a little bit by inserting this oxide layer between the semiconductor, P-type semiconductor for definiteness, P-type, and the metal, which is the gate. And the semiconductor is, of course, the body. Let us assume for now that the semiconductor and the gate are kept at the same potential. So the voltage between the two is zero. Now, how can you maintain zero voltage between two objects which are separated by the electric layer? Well, you connect them with a wire, right? So there is a wire which connects the gate and the body. And through that wire, the two objects can exchange electrons. When will they stop exchanging electrons? Well, when their Fermi energies will level off. Okay, they come to equilibrium with each other, to chemical equilibrium with each other, chemical potential, the Fermi energy. Same thing. Good. So as a result, Fermi energy becomes the same. Now we have the vacuum energy. This is the vacuum energy on the metal side. This is the vacuum energy on the semiconductor side. And this is the vacuum energy in the oxide. The energy difference between the vacuum energy and the Fermi energy is called the work function. The work functions of the metal and of the semiconductor are different. Yeah? And this means that the semiconductor bands must bend. Okay. So the vacuum energy must be a continuous curve. On the metal side, the vacuum and the charges practically do not redistribute themselves because on the metal side, the concentration of charges is astronomically huge as compared to the semiconductors. So the metal dominates in terms of the leveling of the energies. The semiconductor must adjust itself to the metal, not the other way around, because the metal has so much more electrons. And the semiconductor adjusts itself by redistribution of its majority carriers, holes in this case, and this redistribution results in the band bending of the semiconductor. So the semiconductor, we assume in this diagram that the semiconductor work function is higher than the metals. This is not a necessary assumption, but okay, let's assume that. So the semiconductor bands have to bend a little bit. The Fermi energy is constant throughout the device. This line represents the intrinsic Fermi energy in the semiconductor, and I take it to be right in the middle of the band gap. There are no relevant bands in the dielectric. We do not care about the bands in the dielectric, but there is a constant electric field in the dielectric, right? Because in the semiconductor, you may have non-zero charge density near the surface. For example, this is the surface charge density of the depletion layer, and plus during this technological process of making the MOSFET device, the interface between the semiconductor and the oxide contains a small number of trapped positive charges, ions. So trapped charges at the interface, which also, so which means that this dielectric layer acts as a capacitor, and the plates of this parallel plate capacitor are charged. So here you have some charges, and then here you would also have some charges due to, so that the whole structure is electrically neutral. So we have this parallel plate capacitor. The plates of this capacitor are charged, which means that a constant electric field exists inside this capacitor, which means that the electric potential changes linearly inside this capacitor, which means that the electron energy changes linearly inside this oxide layer, inside this capacitor, which means that the vacuum energy on the within the oxide also changes linearly. So hence this is the straight line. Okay, so that's the logic. Okay, I told you. Yeah, I told you everything from this slide, it seems. All right, good. Moving on. Moving on. The last slide in this lecture, the energy band diagram. Now let us apply a voltage V sub GS between the gate and the source, the gate voltage. Okay, so as I said earlier, I will sometimes use V sub GS, sometimes I will call it V sub G because I would forget about the S, no intention, but since the source is grounded, the potential of the source is zero, so it doesn't matter if you write an S subscript or not. The important thing is the G subscript because it tells you that this voltage is applied to the gate. Good. So let's say I am applying a positive voltage to the gate. What does it do to the electron energies? It lowers the electron energies by the amount elementary charge times V sub G, but times the gate voltage, right? Because the energy of an electron in the region where the potential has the value phi is negative E phi. So application of a positive voltage Vg to the gate lowers the metal energies, the vacuum energy, the Fermi energy by the amount is E times V gate. Good. And now let us express now the last logical step in this slide and in this lecture really is to express the semiconductor work function in terms of these parameters, all parameters that we can see in the diagram. So we can express the semiconductor work function, the difference between the vacuum level right here and the semiconductor Fermi level. So this is Fermi level on the semiconductor side. It said I paused doing something. I hope the recording is not paused or sharing not paused. All right, okay. Yeah, sorry about that. So the semiconductor work function is the vacuum energy minus the Fermi energy on the semiconductor side. Or you can write it as the semiconductor affinity, E chi semiconductor, plus the energy difference between the conduction band H energy and the Fermi energy, this energy difference. EC minus E Fermi, this is this energy difference, plus electron affinity, this energy difference, is this energy difference the work function of the semiconductor. Now, let us express the work function of the semiconductor using the parameters seen in the right part of the diagram, that is, using the parameters of the metal, of the gate, of the metal, and of the oxide layer. All right, so if we add electron metal work function, psi metal or E psi metal, plus the voltage drop across the oxide layer, EV oxide, plus the surface potential in the semiconductor. This is the surface potential of the semiconductor. Then we will get from here, from this point to this point. Okay, so then we will obtain the difference between the vacuum energy on the semiconductor side and the Fermi energy on the metal side. Okay, so this energy difference is this metal work function plus this oxide voltage plus this the surface potential of the semiconductor. But we are interested in the energy difference between, in the semiconductor work function, in the energy difference between the vacuum energy on the semiconductor side and the Fermi energy in the semiconductor side, not in the metal side. Now, since we have applied the voltage to the metal, to the gate, then the Fermi levels of the metal and the semiconductor differ from each other by the amount elementary charge times the gate voltage. So we need to subtract this energy, elementary charge times the gate voltage, to get the energy difference between the semiconductor Fermi between the vacuum energy on the semiconductor side and the semiconductor Fermi energy. Okay, so E psi metal plus EV oxide plus E phi prime semiconductor is the energy difference between the vacuum energy on the semiconductor side and the metal work function. But now we subtract from that the gate voltage multiplied with the elementary charge, and we get the energy difference between the semiconductor vacuum energy and the semiconductor Fermi energy. Okay, so this is the energy balance equation obtained just by inspecting the energy band diagram. And using this relation, we can express the gate voltage in terms of everything else. So you just rearrange the terms in this identity, okay, the one around which I'm moving the mouse. And so this gives us the gate voltage in terms of everything else. And this is a fundamental equation which can be used to derive the threshold voltage and also another interesting voltage, which is called the flat band voltage. That is the voltage you need to apply to the gate to make sure at which the semiconductor bands do not have bending, they're flat. But we will do this in the next class. For now, thank you all very much for your kind attention, and I'll see you later. Goodbye.